Hey guys, so in this lesson or in this review, we're going to be looking at this objective 6, where we are sketching and labeling the graphs of exponential functions or inequalities. We're not really going to be looking at the more inequalities, more exponential functions. And then also beginning to look at this number 7. This will come up more later as well, but looking at the characteristics, so like intercepts, symmetry, increasing and decreasing, maximums and minimums, continuity, zeros, domain and range, and any possible restrictions that it may have. So we're going to kind of link it with other graphs that we've talked about. You may be familiar with graphing these. There will be a lot of connections with what we've already done with rational functions. So feel free to pause the video and try it without first, and then just use the video to check your work and clarify any misconceptions. I do believe that many of you guys would have a general understanding of what to do. So if you can start with following along, this is going to be a shorter lesson with me on these 2 pages about graphing exponential functions. So exponential functions. So I'm starting with this one right here, y equals 3 to the power of x, and I gave a table to kind of fill in. So think through the properties. If you have 3 to the power of negative 3x, that's 1 over 3 cubed, which is 1 over 27. It's a pretty small number, right? And then when you plug in negative 2, 1 over 3 to the 3 squared is really what's happening, right? So here, I'll even write this. 3 to the negative 3 equals 3 to the negative 2 equals. So, which is 1 over 9. So getting a little bit bigger, right? We're dividing it by 3, I guess is the way to say it. I'm sorry, we're multiplying it by 3. Let's see. 3 to the power of negative 1 equals 1 over 3 to the first, which is 1 over 3. 3 to the power of 0, that's just 1. 3 to the power of 1, 3. 3 squared, 9. 3 to the power of 3, 27. I might not be able to graph them all, but that's okay. We'll get the trend of this. So if we plug in negative 3, we get a really small number right here. If we plugged in negative 2, it's going to be slightly above that. If we plugged in negative 1, it's going to be slightly above that. I'm not very great at drawing this. If we plugged in 0, we got 1. 1, we got 3. 2, we got 9. 3, we're off the page. I'm not going to graph the whole thing. So if you think about it, if we keep making that number smaller and smaller, we're never actually going to get to 0. Right? Like think about dividing by 2. Like if you keep cutting something in half, you're going to get really, really close to 0, like arbitrarily close to it. We're never actually going to touch it. That is, and we're coming off of a unit where we talked about asymptotes, that is an asymptote. Right? So it just gets exponentially, got it, close to that line. So here we have an asymptote. So we're actually, in this case, not going to have any x-intercepts. So I'll label this. This is the line y equals 0. Right? Think about horizontal asymptote. And I think I'm going to label this point as 0, 1. So we see the y-intercept. I think that's an important one. So if we're looking at the domain, are there any x values we can't plug in? No. Like x can be all real numbers. It can be anything. The range, however, in this case, it's never going to go below 0. It's never even going to get to 0. So it's going to be from 0 to infinity. Right? Notice I'm not including it because it's not inclusive of that. Some of you guys might be writing y is greater than 0. That's acceptable also, but keep in mind, like, it's not equal to 0. X-intercepts, we kind of just spoke about this. None. Y-intercept, and that won't always be true, right? When we start looking at shifts, which is not in this lesson, you can, like if you shift it down, you might have an x-intercept, and we will be looking at that, but for right now, it's not going to. So the y-intercept, 0, 1, that's when I'll write it, it's when x equals 0, and this is when y equals 0. Right, just to reiterate that. Concavity, this was going to be concave up. Right, look at the curvature of it. So it's going to be concave up on the entire domain. So it's going to be concave up from negative infinity to infinity. Asymptotes, so you've got 1. We labeled it on the picture, which is helpful. Y equals 0, and I'll say that it's a horizontal asymptote. Exponential functions actually won't have a vertical asymptote, but their inverse will, which is what we're going to be learning about a little bit later. Increasing interval, as you go from left to right, how quickly it increases changes, but it's increasing the entire time. So the increasing interval, negative infinity to infinity. The entire domain, decreasing interval, never, for the empty set. This is an example of what we call exponential growth, right? Because as input gets larger, output gets larger. Or as x increases, y increases. Exponentially, right? Like in this case, like every single time it's getting bigger. In this example, multiply y by 3 for each change of x. Right, so it's like you're tripling it every single time. So it's going to grow really, really quickly, exponential growth. Let's take a look at the one in the back. Oops, sorry, you can kind of see through it. So here I've changed a little bit, so you can see I have 1/3 to the power of x. So if you do 1/3 to the power of -3, think about, oh, you're distributing that. So that's like 1/3 to the power of -3, which is 3 to the power of 3, which is, oh, look at that, 27. It's a pretty large number. Here, you've got 1/3 to the power of -2, which is going to be 1/3 to the -2, which is 3 squared, which is 9. Got a little bit smaller. 1/3 to the -1. 1/3 to the -1, which is going to be 3 to the first, or 3. Look, we're dividing by 3 each time. It's clearly getting smaller. What about 1/3 to the power of 0? Anything to the power of 0 is just 1. 1/3 to the power of 1. Anything to the power of 1 is just itself, 1/3. 1/3 squared, 1/3 squared, which is going to be 9. I'm sorry, 1/9. That's terrible. Oh, that's upsetting. 1/3 cubed, which is going to be 1/3 cubed, which will be 1/27. Right, so as you can imagine, like, what did we just do to the base? We just changed it to have a power of 1/3. I'm sorry, a base of 1/3 instead of 3. You mean a fractional base that's between 0 and 1. So if we're going to graph this, I'm not going to graph that -3 because I don't have 27 spots. But I'll start with -2, 9, -1, 3, 0, 1 again, and then 1, 1/3, 2, 1/9, 3, 1/27. So you can see it's getting smaller this time. So again, like, no matter how I change that exponent, it's never actually going to get to 0. I'm still going to have this asymptote here, which I will graph and label. And I will also label this point as 0, 1. So I do want to stop momentarily, and I want to think about, this is also the same thing as 3 to the power of -x. And I think that's important to generally know that these two are equivalent to each other. So it means the same thing. As far as domain, again, x can be anything. Your domain is going to be all real numbers, or negative infinity to infinity. Your range it's still going to go from 0 to infinity. That's not changing. So either 0 to infinity, non-inclusive of 0, or if you want to say y is greater than 0, also non-inclusive of 0, great. X-intercept, we still have an asymptote there. There's still none. It never crosses the x-axis still. Again, when we start shifting and moving, or that will happen. The y-intercept, still 0, 1. That didn't change. Concavity, it's still concave up. Asymptote, it's still at y equals 0. Increasing interval, now that's never happening. It's never going to be increasing. It's decreasing over the entire domain if we look at it, right? You go from left to right, it's dropping, maybe at a different rate, but it's constantly dropping. It's continuous too. Decreasing interval, the entire time over the entire domain, so from negative infinity to infinity. So if you think about what just happened, we went from 3 to the power of x, and it looked like this. And then we did something to it, and we had 3 to the power of negative x, and it looked like this. It had almost all the same properties. It just looked different like that. So I can't really, can I graph them on top of each other? Let's see, do I have another one? So if I graph them on top of each other, I would have, I don't know how great this pen is. Not so great, let's see. Do we think this one works? Kind of. I should have brought more pens home. Yep, not so great. I should probably throw this one out. Oh no. It's okay. That's as good as it's gonna get. You think I can highlight it? No, it's not gonna be effective. I'll try one more pen. Maybe this one. Not great either, but maybe you kind of see the point. So as you can kind of see, what happened was it reflected over the y-axis. Right, so it's a very interesting to take a look at this, and you can connect it back to geometry, you can connect it back to probably things you learned in Algebra 1, things we learned in other units, like even when we were talking about lines and parabolas. When x becomes negative, it is going to reflect over the y-axis. It's like a rule to be recognized where you won't always have to graph it. And so that's where it became important for us to recognize that, well, 1 over 3 to the power of x is the same thing as 3 to the power of negative x, because we could have generally known what this was going to look like in relation to the first function we dealt with before we even did this. Good connection to make. So if we just look at the end of this right now, so this is an example of what we call exponential decay. As x increases, y is decreasing. And not just decreasing, it's being divided by 3 or multiplied by 1/3, which is the base, right? So on both of them, you can see whatever the base is that number that you're being, it's like the multiplier. When you're dealing with exponential functions on the other side, you were multiplying by 3 every time, and it was getting bigger. In this case, you're multiplying by 1/3, it's getting smaller. It's continually being cut by 1/3, so it gets exponentially smaller. Great, so what we just did in this brief lesson, we didn't look at any transformations, that's what we'll do next. What we did was that we sketched and labeled some graphs of exponential functions. We did not look at inequalities. We didn't really do too many variety of bases. That's what you'll have for some extra practice with this. And we started to look at some of the characteristics, maybe not all of these, and that will come up more when we start looking at the translations, which we will do next. If you have any questions, again, please let me know. Otherwise, keep practicing and use the extra resources for that.